Hello, friends. Electromagnetism and fluid flow, these two are completely different branches of physics. Electromagnetism is mostly concerned about the effect of electric and magnetic field on the motion of charged object, electromagnetic wave, etc., where fluid dynamics focuses on the motion of objects through different kind of fluid flow, etc. But many idea of fluid dynamics played a crucial role in the development of the Maxwell's equations, which are the four fundamental equations of electromagnetism. In today's video, we are going to have an insight of the relation between these two completely different branches of physics. Before discussing the main topic of the video, let's consider an example. We are all familiar with black hole, right? The celestial object with crazy mass density, which creates gravity so immense that it literally devours anything in its vicinity. White holes are opposite in nature. Theoretically, white holes throw up matter and energy outside. Although there is no actual evidence of white holes unlike black holes, there is no harm imagining it. Let's imagine a white hole which only splashes out matter. To make it simple, let's consider that it kind of radiates water uniformly in all directions, and its water generation rate is constant. Now we want to calculate the water or fluid generation rate of the white hole. That is, what is the total amount of matter it generates per unit time? For that, first let's consider a frame which is situated inside a river where the velocity of water is the same everywhere. We can easily figure out the amount of water flowing through the frame per unit time. It is the dot product of the area vector of the frame and the velocity of water. Now let's consider a similar frame at some distance from the white hole in our example. In order to calculate the water flow rate throughout the frame, we need to consider the frame sufficiently small, because as we saw earlier, the velocity of water throughout the frame needs to be same to apply the formula we learned previously. If we consider the frame infinitesimally small, then the velocity of water throughout the frame will be equal. Then for this infinitesimally small frame, the water flow rate through it is this. Now let's envelop the whole white hole with this tiny frames and sum up water flow rate through each of them. What do we get? We get the total amount of water flow rate throughout the entire surface, which is exactly the rate of matter produced by the white hole. Notice that shape of the enveloping surface doesn't matter as long as our target source is completely covered. To calculate the water production rate, we need to calculate this integral here. In vector calculus, this kind of integrals are called surface integrals. Now, before we actually calculate the integral, let's first have a look on some facts. This might be the hardest part of the video, so make sure to provide full concentration. Let's consider the shape of our white hole to be arbitrary. Here, these water particles right on the surface of the source all will have the same magnitude of velocity perpendicularly outward of the surface, which was our assumption. We are also considering the motion of the source to be zero. That is, no linear or angular momentum for the source. That means the center of mass of the source is fixed at its original location. So, in order to obey the law of conservation of momentum, the particle on the surface should move such a way that the center of mass of this batch or group of particles coincide with the center of mass of the source, which means this batch of the particles will make a surface while moving, and throughout this surface, every particle will have the same magnitude of velocity. Because if they don't, then the center of mass of the particles on that surface will start to shift from the center of mass of the source, and the center of mass of the source will also start to shift from its original position, which will contradict with our assumption of the center of mass of the source to remain fixed. Simply, the point of all this discussion is that there will be surfaces throughout which the water particles will have the same magnitude of velocity while being drifted away from the source. And if the source is spherical, as we considered for our white hole, then the surfaces throughout which the magnitude of velocity will be the same will also be spherical, because the center of the spherical source and spherical surface will always coincide. Now finally, we are ready to calculate the surface integral. As we know that the shape of the surface doesn't matter to calculate the surface integral, as long as we totally envelop the source completely, so let's consider the surface to be a spherical surface. Because as we know that all the water particles on a spherical surface will have same magnitude of velocity perpendicularly outward of the surface, it makes the calculation of the integral easier. Here you can see the calculation. Now let's make an interesting observation. Let's consider two surfaces with radius r1 and r2. As the same amount of fluid is flowing through each of the surfaces, we can equate them. After a bit of calculation, we get r1 squared times v1 is equal to r2 squared times v2. That means we can write v times r squared is equal to some constant k. We can also write v is equal to k divided by r squared. That means in this setup, the velocity of the fluid will be inversely proportional to the square of the distance from the origin. If we construct the vector field of this nature, it will look like this, where the velocity of any point is given by this expression. Now here comes the interesting part. Look closely, isn't this form of vector field quite common in nature? For gravitational field, we have this expression where for the given mass, the numerator is constant, and we get the same pattern. For electric field, we have this expression where we also see the same pattern. Because this pattern is quite common in nature, it has a name. It is called the inverse square law. But for our original example, there was a real physical fluid flowing throughout the space. The math tells us that there must be a kind of fluid flow responsible for the electric field. Although we can't feel it, but its effects are real. So physicists named this special kind of fluid electric flux, where the word flux basically means flow. We can calculate the total flux the same way we calculated total flow rate of water previously by this surface integral. Just simply replace V with E. Also note that electric flux also depends on the amount of net charge the source contains. From the equation of electric field, we see that magnitude of electric field is directly proportional to the amount of net charge contained in the source. So we can say electric flux is also proportional to the net charge contained in the source. If we get rid of the proportionality sign and use a proportionality constant, what we get is Gauss Law, one of the equations of Maxwell's 4 fundamental equations of electromagnetism. So, that's it for today, guys. If you like this video, please give me thumbs up and subscribe to the channel. Let me know your opinion in the comment box below. See you until next time. Goodbye.